William, you had a question? Where's your question?
Well, it has something to do with open stacks.
All right, go ahead.
It's the first one that has something to do with using the information acceleration and velocity.
Why don't you pull it up? Okay, can you pull it up and show it to me, Justin? Can you pull it up?
Question. It's number 6. It has nothing to do
In open stacks or?
in open stacks.
Okay.
It has nothing really to do with the work. What is 1 radian approximately in degrees?
Right. So remember, you're going to have to do this on the exam where you have to convert units. So make sure that you're able to do that because it's going to happen several times. And you just need to remember your conversion factors, that 1 revolution is 360 degrees is 2 pi radians. And so if I'm looking at a radian, you know, I start with 1 radian, and then I know that in, was it degrees?
Yeah.
So you convert it to degrees. You have 2 pi, 360, and you know what's that? That's about 360 over 6, about 60 degrees, about. What? Like that?
The problem is the closest one to that was 57.3.
Well, I don't know. What is this? 360 divided by 2 pi. That's probably about that. I don't know.
The first question says a fan spins at 6 revs per second, and when I turn it off, it slows at a rate of 1 rev per second squared.
Okay, so I'm looking for an angular displacement. No. So I'm told that I'm looking for theta, right? I'm told that the alpha is 1 revolution per second squared, but in that problem it said that it's slowing down. That means that alpha is going to be opposite the direction of omega, right? Alpha is our acceleration, omega's our velocity, so I'm going to make this a negative. And what was omega initially equal to?
6 revs per second.
6 revs per second. And it wants to know how far does it travel in the time that it takes to stop. So omega final is equal to 0. Am I right? That's what the question is asking?
It's asking for the angular displacement before it stops.
Before it stops. So this, in order to find the angular displacement, you say theta is omega naught t plus 1/2 alpha t squared, right? But I don't know what theta is, and I don't know what t is. And so you sort of freak out a little bit, and you say, oh no, what am I going to do, right? Did you freak out a little bit?
A little bit. I was contemplating with myself whether I should cancel out the t's altogether.
No, you can't cancel out the t's. How do you find the time? How do you find the time in this case?
You use the other two.
Right, I use the other one, right. I always like to write both equations off to the side, or you have your equation sheet. I say, well, I also know that omega is equal to omega naught plus alpha times t, and so omega is 0. That's 6 minus 1 times t, so it takes 6 seconds for it to stop. And then I can come in and calculate what theta is, because now I know what t is. There's a similar problem in your homework assignment. Sorry, you get all the assignments. Y'all probably don't look at those questions that much, so they're good questions to look at if you need additional practice. The problems in the workbook, sort of in the back of each chapter, there's some problems like that. These are 2 set problems. They're not 2 systems. They're not a system of 2 equations. That is where you have 2 equations with 2 unknowns. But it is a level of algebra that I want you to be able to do these tests. Okay. Right? Does that answer your question? Yeah? All right, what else we got? Any particular questions?
Is the answer to that?
I'm not going to work it all out. I want you to go and I want you to find out what theta is. And I don't remember if it was given in revolutions or radians, but
If the answers are yes.
okay. So remember, when your kinematics equations, you can keep those answers in. You can keep your units in revolutions or degrees or radians. It doesn't really matter. But when you're dealing with other equations, like relating your linear and your angular quantities, remember these equations, S equals theta r, V is equal to omega r, and A is equal to alpha r. In all of these, the quantities have to be in radians. Okay? And then what else? When we're dealing with torques, like later we're going to see torque is equal to I alpha. This always has to be in radians. We're going to see that. We might actually get to that a little bit today. All right? So this week what we've seen is we saw kinematics. That's where we were dealing with these equations. Theta equals omega naught t plus 1/2 alpha t squared. And omega equals omega naught plus alpha t. That's what we've seen. We also saw how to relate the linear and the angular quantities. Remember, so for example, if I have a tire that's rotating with omega 1 revolution per second, for example, and I want to know on a particular point on that tire, what is the linear speed of that point? And let's say that the radius here is 2 meters. It's a big tire. It's a 12-foot tire. That's something, isn't it? Then V is equal to omega times R. So that would be 2 pi radians per second. Why did I write 2 pi? Right, it's a revolution, right? There are 2 pi radians in 1 revolution times the radius, which is 2. So that would mean that the speed is 4 pi meters per second, or about 12 meters per second. So you'll need to know how to relate those linear to our angular quantities. And as I said, S is equal to theta r, V is equal to omega r, A is equal to alpha r. We can always relate, it's an alpha, relate those angular and linear quantities. And then also, we saw the concept of centripetal acceleration, V squared over r. And we saw this in a couple of different ways. Like, for example, on your OpenStax, there's a question where you have a car going around a curve like this, and you have to find out what is the coefficient of static friction, or what is the frictional force. And you need to recognize here that the frictional force, Fs, that's the force between your tires and the road. Your total frictional force is equal to mass times the centripetal acceleration. That is our centripetal force. Okay? And that's causing a change in velocity. It's causing an acceleration. I can do then that Fs is equal to mv squared over r. We can look at one of these problems if you want, though we did one in class, if you recall. And then we can go from there and figure out, like on that OpenStax assignment, Fs is equal to mu s times the normal force, which is equal to m times g, and that's equal to mv squared over r. Okay? And we did that? Listen, I didn't do this week, but I want to touch base on it, and I'll come back on Monday with the class and touch base on this. I just forgot, and I didn't have it in the workbook, but I usually do it extra. You'll probably see it on the test. You won't see this in the OpenStax, but it's fairly common in physics courses to look at like a car, for example. Now I want to imagine that I have a car right here that is on an embanked curve. So what you're looking at right here is the front of the car. So let's put the headlights on it. Does that look better? Does that look like a car?
Somewhat.
It's coming towards you. Yeah, and it's coming towards you. Those are the headlights, and the wheels are the little lines on the side. Goodness, and it's coming towards you. You okay?
I'm good. I just had something in my throat is all. Probably changing the weather. It's probably the sun changing weather is causing.
Yeah, or it could be a nutria.
A nutria, sir?
A nutria.
Nutria. Goddamn rat.
All right, let's watch our language. All right, so anyway, I have this car and embanked curve. Now, usually it's just the frictional force that's causing this change in velocity. But in this case, what is the force that's causing a change in velocity? Well, let's try drawing our force diagram, because I have several forces that are acting on this car. I have the normal force, Fn. I also have the weight, Fw. I have the frictional force, Fs. That's it, right? Yeah, that's it. So here, the frictional, what's that? Ah, no. I know what you're thinking, that, because the car, if it's going around a banked curve, don't think of this as an inclined plane, although it is sort of.
It's a banked curve.
It's a banked curve. It's like a cutout. And so if I didn't have the frictional force, what direction would the car travel? Up or down the inclined plane?
Up.
Right, it would go flying off the road. It would go up the inclined plane. It was, yeah, no, it's not parked. It's moving. It's booking it. And that frictional force does play a role in keeping it on the road, but what other force plays a role in keeping it on the road? No, the centripetal force, now be careful, the centripetal force, it's not like I look at this diagram and there's another force that's the centripetal force. Instead, no, there are some force or some combination of forces on this diagram that act as the centripetal force. Now, what are the forces that act, forces that act as the centripetal force? You're right. Oh, close. Not the weight. Because notice the weight is entirely vertical. The weight is only acting in this direction. But I know that my centripetal force is going to be a force that will act in this direction. Right? Now what force or forces make up that centripetal force? Right, the normal and the frictional force, yeah. So the normal force has a component that's in this direction, and the frictional force also has a component that's in this direction. So my centripetal force, Fc, oh, not it, big Fc, is equal to the x component of the normal force plus the x component of the static frictional force. You're not going to see any problems regarding that. They get kind of complicated because you have multiple unknowns and you're dealing with you have to resolve your vectors and all that. But I do want you to understand that on a banked curve, that's why we bank our curves, is because it gives us this additional force. It's not just our static frictional force, but it's also a normal force that's providing the centripetal force. And when you go around a curve, it's the centripetal force that keeps you on the road. Okay? So it allows you to have a higher maximum speed when you have a banked curve. I'll talk about that in class on Monday, so y'all see it again. I just want to give you a preview, okay? All right, what else did we do in that chapter? Okay, yeah, that's chapter 8. We'll get to that. We also talked about, remember, the Ferris wheel or the car moving on the roads. And so, remember here's the car. These are like the Mississippi roads, right? And if I have a guy sitting inside this car, he's got two forces acting on him. He's got the normal force and he's got the weight. And we need to be adept at writing the force diagrams or writing Newton's second law. The sum of the forces is Fn minus Fw, and then that's going to equal to m times the centripetal force. And in this case, that centripetal force is positive. But over here, I have a car. My forces, I have my normal force, and I have my weight. And the sum of the forces here are going to be the same. The normal force minus the weight. But that's going to equal to minus MAC. Why is the centripetal acceleration negative? So here my centripetal acceleration is negative, and why is that? Because the centripetal force is always... That's where you say
the frictional force.
No, it's not always the frictional force. The centripetal force doesn't have to be friction. In fact, here the centripetal force is not friction. But the centripetal force is a force or collection of forces that is always towards the center of the circle. And so the centripetal acceleration is in this direction towards the center of this circle. And then over here it's in this direction towards the center of that circle. Yeah?
So on a flat plane, frictional force can be centripetal force.
On a flat plane, if you're going around a curved surface, yes.
And if it
Or a curve.
If it were an inclined plane and if it were a curve, that means that the frictional force wouldn't be equivalent to centripetal force.
Not necessarily. Like on this one where I have this banked curve, the centripetal force is partly the normal force and partly the static frictional force. Look, the extreme of this is where my embanked curve goes all the way to 90 degrees. And that's like that thing that you ride at the fireman's fair where you stand there and you spin you around, you know what I'm talking about, like a salad spinner. And in that case, what is the centripetal force in the salad spinner? Y'all ridden one of these things before?
Well, the spaceship, right?
I don't know what it's called, but if I have the thing where people stand inside of it, you go inside this chamber, and then it spins around.
Yeah.
What is it, John? The wall, right. So you have the normal force of the wall is equal to MAC. That is our centripetal force. The normal force is the centripetal force. So you need to be able to identify, you'll probably have a couple questions on the test, where you have to identify what is the centripetal force. And these are really the only three situations, you know. I have something on a flat surface, on an embanked surface, and then also in a vertical surface, like the salad spinner at the fireman's fair. They have a salad spinner at the fireman's fair? They do have one. Okay, yeah. Oh, they did. Okay, that was chapter 7. And then today we did chapter 8. We just sort of started on chapter 8. You have any questions? Particular questions?
Maybe asking this too far ahead, but how far into the videos for the answers for exam 4 go back?
How far did the videos?
Go back.
Well, I don't know. Whatever's on there.
Last time I checked, was that exam 3 or like 4?
All right. Well, that's what it is. It's not going to change. I'm not making new ones if that's what you mean. Well, you have the answers. You can certainly practice that. Today we did this, where you have to find the net torque. I think this is, I don't know what test this is, but you'll have some questions like this on the test, where you have to find the net torque. So you need to make sure that you're good at that you can find the net torque. Is this in your workbook, John, or is this different?
It's different.
Okay. Well, that's okay. Let's just do this. So I'm rotating about point C right here. That's my axis of rotation. And you know, I could take this problem on another test and make this the axis of rotation. It would change the way you work the problem completely. Or not the way you work the problem, but it would certainly change the answer. And then right away I say this force, no torque at all. Because if I'm trying to push on the axis of rotation, right, this is my hinge right here, I'm never opening this door by pushing at the axis of rotation because I get no torque on that. So I just say the torque due to this force is equal to 0. And then the torque due to this force, well, is it clockwise or counterclockwise? I always like to take my pencil and put it on the paper. And I hold it like this, and I say, well, if I pull up like this, that makes my pencil go clockwise. And so that force provides a negative torque because it's clockwise. And then the y component of this force, right, this force has a y component. It causes the thing to move in this direction, which is counterclockwise, so it has a positive torque. So my net torque, let me get you here. My net torque is the sum of all the torques is going to be negative the blue torque plus the red torque. Or we'll call this torque 1 and this torque 2. So it's going to be negative 20 newtons times 1 meter, because 1 meter is the distance to the axis of rotation, plus 10 newtons times what? 3 meters, that's this distance. Thank you, Drew. Times sine of 30. Don't forget that sine term. And then whatever that is, let's see, that's 20, 30, 15. That's negative 5. So it's 5 Newton meters clockwise. Yeah, that's right. 5 Newton meter is negative, so it's clockwise. William?
Isn't clockwise?
No.
No, clockwise is negative.
Clockwise is negative. So
Counterclockwise.
remember I told you you can order those clocks from like the geek store, the geeky science catalogs, where they have the hands that go backwards because that's the positive way for rotation.
I actually thought that torque 2 was actually going clockwise.
But torque 2 is counterclockwise, yeah. All right. Students have trouble with that, so make sure that you practice sort of looking at forces and figuring out is this a positive or a negative torque, because I know that some students will miss that question because of that.
So how come it's clockwise when it's the second torque?
This one right here, it's not, it's counterclockwise. This one's counterclockwise, and so this torque is positive because counterclockwise torques are positive. In general, when we're talking about rotation, counterclockwise is positive and clockwise is negative.
I'm just trying to figure out the transition from one torque to another.
I don't understand.
That's what I like the change from straight up to clockwise force.
This force causes it to move in this direction. This force, that is clockwise, but this force causes it to move in that direction. That's counterclockwise. All right. You'll also have some balance of torques, like this number 26. But once you do these once, they're fairly easy, I think. Where do you place the 2 kilogram mass? Well, you just say the torques on this side have to equal the torques on that side. So I would say 20 newtons times x, 20 newtons, that's the weight, right, has to equal 10 newtons, that's the force of a 1 kilogram, times 2 meters. And so x would equal to 1 meter. Hopefully those are easy for you. Later we'll get into some where you have to find the balance of torques and it gets a little more complicated. But as a first pass, you'll have probably one question like that. Alrighty? What else in particular were the stuff that we were doing today? Any particular questions about those things? Yeah, Seth? When to put an angle or not. So I didn't put an angle here. It's sort of implied because my force is in this direction and my moment arm is here. And my angle between those is 90 degrees. But the sine of 90 is equal to 1. So I didn't put an angle, and I did. It's equal to 1, so I don't need to write it. You'll get the hang of that. You always need to practice. You need to practice writing that, calculating the torques, and finding the next torque. Yeah, of course. Yeah. All right. Here's for the experience. Okay. Well, let's look at some of the homework questions. Oh, no, what's that? Go what now? This one I was looking at? Oh, number 27? Yeah. I like these ranking questions. These all have the same magnitude of force applied to them, and I want to know which has the greatest torque and which experiences the least torque. Remember, with torque, there are three things that affect torque. There is the force, the moment arm, and the angle theta. Now in this one, the force is constant. We say the forces are all the same. But R changes and theta changes. In general, or not in general, always, as theta approaches 90 degrees, the torque gets bigger, right? You get your maximum torque when your angle is 90 degrees. So like when I open a door, it's better for me to push like this. Out at a big R, if I try to open here, it's harder for me to open. And then also, if I try to open it like this, at a shallow angle, then that's harder. I want to open at a 90-degree angle. That's the easiest way. I get the most torque on it. And so the one that has the biggest R and the angle closest to 90 is the biggest. So that's number 3, has the biggest torque. Get rid of B and C. And then the one with the least torque is the one with the smallest moment arm at the smallest angle. Which would that be? It's either 4 or 2. Right, it's going to be 4. So D is wrong. You'll certainly see a question like that where you have to rank torques. If you look back at some of the old tests, I have one like that on almost every test.
Yeah, I put a board and put a little dot and just make it a ring.
Okay, all right. Yeah. It's easier when it sort of makes sense. I understand.
It's this. Right.
All right. Let's look at some of those homework questions from 7 and 8. Y'all have plans for this weekend? Do you work as a nurse?
Yes.
You still as a nurse, okay. What job? Rest of you. Huh?
In New York.
I hope not. I hate hospitals. Oh, you were joking. Yeah. Yeah. I don't like hospitals at all. Let's see. So this is in your workbook. Let's look at this one. So here I have a person's arm, and I want to know what force must be exerted by the bicep in order to hold up this carton of milk. And I'm told that the milk is 2 kilograms. So that means that the weight of that milk carton is 20 newtons, right? 2 kilograms, 2 times G gives me 20 newtons. And I want to know what must FB be, that is your bicep, what must it be in order to lift this carton of milk. Listen, the bicep forearm arrangement is a very inefficient lever system. What is it? A class 3 lever, I think. I forget what the class is, but the way that it's set up, it's not a very efficient lever system because you need a really big force here to lift something that's relatively small here, because my moment arm for the bicep is relatively small, but my moment arm for whatever's in your hand is relatively big. That's why guys get these really big biceps, because you just need it to lift things. You need big muscles to lift even moderately small things. So what I would do is I would say that in order to lift this, I need to have it so that the sum of the torques equals 0. Because if the milk carton is too heavy, it's just going to make my arm fall down. And the sum of the torques, well, let's see. This force, FW, causes it's going to make it go like this. It's counterclockwise, causes a positive torque. I'll call that positive torque 1. And this force, FV, I'll call it torque 2, is a negative torque. Is that right? Yeah, because this force causes it to go this way. My axis of rotation is here. This force pulls it up in this direction. This force pulls it in that direction. Counterclockwise, clockwise. And so my net torque is going to be torque 1 minus torque 2. And that has to equal to 0. Now I can put in my torques. Fw times 32 centimeters minus Fb times 8 centimeters times the sine of not 30. Guys, I don't do this anymore, but on tests, but sometimes you might encounter this, that I really need to know this angle right here. And so that angle is 60 degrees. But I don't do that on tests. I always give the angle with respect to the moment arm. But here, that angle 30 degrees is given with respect to the normal, the perpendicular line. Y'all see what I'm saying? Yeah, so if you encounter that, just keep that in mind, but you won't see it that way on the test. And so that's sine of 60, and that's equal to 0. And then I can solve for Fw of this. I can solve for this. So that's going to be 20 times 32. Notice I didn't change my units because those units are going to cancel out anyway. So I can keep that in centimeters. But if that bothers you, let's just change it to SI units. Yeah, let's just change it anyway. Minus this isn't FW, this should be FB. FB times 0.08 sine 60 equals 0. And then I solve for FB. That's going to be 20 times 0.32 divided by 0.08 divided by sine 60. Uh, 92 newtons. Is that what y'all got? 92? Yeah, awesome, Sean. So that's 92 newtons. You got to exert 92 newtons to lift a 20 newton milk carton. That's a factor of 5 more. So if I wanted to lift 100 pounds, that would be a lot actually. But if I wanted to lift 100 pounds, I'd have to exert 500 pounds of force from my bicep. Wow. Isn't that something? And with your deltoid, it's even worse. Because if you think about how the deltoid muscles are set up, you have these muscles that come and attach onto your arm, and they attach sort of right here to lift your whole arm. And in this case, you got a tiny little moment arm, because it's just, it's just attached over this distance to lift something that's really long. And then you also have it, what? What else is small in this case with the deltoid muscle? Know what I'm talking about? With torque, I can only have F, R, and theta. So what's small? Huh? The angle, right? The angle is also small. At least with the bicep, you're acting at about 90 degrees. And so you don't lose torque based on your angle. But with the deltoid muscle, you have a very shallow angle, which is why your deltoid is a very large muscle. Because it needs to be to lift that arm. So the levers in the body, they're good for some reasons, but for this reason, they're not very efficient because it requires a big force to pick up something relatively small. All right, let's just do one more. Unless you have particular questions you want to look at. Let's look at this moment of inertia problem. We did one in class like this today. And we're going to, next time, we'll look at moments of inertia for non-regular objects, or not discrete particles. But for now, I want to look at the moment of inertia for these 3 different axes. I can calculate the moment of inertia for an axis that goes, for a rotation axis that's there. And that moment of inertia, remember, I is the sum of mr squared. That's going to be 3 kilograms times 3 meters squared. So what I've done is I've taken this mass and I multiplied it times this distance. This total distance is 6 meters, so I know this is 3 meters. Plus 2 kilograms times 3 meters squared plus 2 kilograms times 3 squared plus 4 times 3 squared. And so my moment of inertia is equal to 3 times 9, 3, 5, 7, 11, 99. What do you think would be the moment of inertia if I went through an axis along the y-axis? Would it be more or less? Would the moment of inertia through the black axis be more or less than the pink axis? Y-axis. You're right. Right, because my particles are closer to the axis. And remember, it's a lot easier to move when I'm rotating really close to the axis than when my mass is out at big, far away from my axis. We'll see that a little bit later next week when we do momentum. So, but I can show you, if I'm looking about this axis, it's going to be 3, or excuse me, not that axis, the black axis. It's going to be, the pink axis, right, we're doing now? Oh, shoot, now, yes, the black, yes, thank you. 3 times 2 squared plus the other 3 terms, 2 times 2 squared, 2 times 2 squared, 4 times 2 squared. Each mass times the distance to the axis of rotation, and so that's going to be 36 kilogram meters per second, meter squared. So I get a significant drop in my moment of inertia, almost a factor of 3, just by changing the axis of rotation. We'll see that when we get to regularly shaped objects. Spheres, long bars, cylinders, they all have slightly different moments of inertia because of the way that the mass is distributed through them. I think you guys will have to get to derive moments of inertia. That's kind of fun. You get to use calculus in a way that you haven't before. Yeah.
So the meters changes to 2 meters?
No, that's meters squared. Because remember, moment of inertia at its very basic level is the sum of mr squared. And
So what was changed in part B?
Oh, I just didn't write it all out. So I was just being lazy. It's 3 times 2 meters, because this is, this distance is 2 meters, plus 2 times 2 meters squared, plus 2 times 2 meters squared, plus 4 times 2 meters squared.
So where do the 2 meters come from?
The 2 meters is this distance. It's the distance from where the object is to the axis of rotation. Alrighty? A question, John? Alright, we'll do another, I don't know, will we do another? We might do a help session earlier in the week next week, Thursday or whatever, since it's the week before Thanksgiving. If y'all want to come late, you just let me know.
Okay.
I'm here for you.
It's going to be the same day, like on a Friday.
Next week, probably not. It'll probably be
Okay.
Thursday.
And,
Alright.
and the 3 meters came from where? 3
meters, right here, we were going around this axis, and this distance then is 3 meters.
So what lines are they